Okay, so this is just the last section about these sort of alternate axes, alternate ways of graphing that we're going to look at. We saw parametric graphing and the calculus behind that, and then now we've seen polar functions and their graphs, and now we'll take a look at some of the calculus behind that. I guess we've already done the differential calculus, at least behind that, finding the slopes of the tangent lines to those types of functions. Now we'll look at the integral calculus of that, and that's the areas and arc lengths and stuff like that. Okay, so first of all, the area of a region in polar coordinates. The way this works, you have a polar defined function, and remember how those kind of generally work. So suppose that's your polar defined function. The way that we kind of view these is that they're defined between two values of theta, just like when we talk about finding the area under a Cartesian defined function, we talk about being defined between two x values, right? So here we're going to be looking at two different theta values. So what you kind of have to picture here is that, like, here's the theta 1, and that function starts right there. Let's say that's a given domain or something like that. And then as theta sweeps out, right, the radius of the function is defined by some formula, right? R equals f of theta, right? Because remember, that's the way we define these types of functions. And then it ends at this other angle that we'll call theta 2. And so theta 2 would be like that one right there. Okay, so the way that we approach these, I think they typically call these just A and B, but they are theta values, they are angular values. And so the way that we approach this type of thing is, if you remember the way that we approached finding the areas under rectangular defined functions, we divide it up into some certain number of subintervals. We're going to do the same thing here. What we're going to do now, though, is look at just a small slice. In fact, really what we would be doing is we'd be dividing this up into a whole bunch of little angular slices, basically, something like this, okay? And so that little distance there is actually a delta theta, not a delta x, okay? And then what we need to remember is that, recalling from trigonometry, there's a formula that tells us the area of a sector. You might not remember that because it's a pretty short little blurb in your trigonometry class or your pre-calculus class, but it was there, the area of a sector. And by a sector, I mean what we're talking about is if we have like the unit circle, or any circle really for that matter. When we talk about a sector, we're talking about like something like that, right? So a little pie piece basically, okay? And so that has associated with it this length here, that was called the arc, the length of the arc. And then we had an angle theta here associated as well, and then we had a radius r. Okay, and so if you remember, for that type of situation, the area of the sector was equal to 1/2 r squared theta. So that just works for, like, if you just have a circle, right, and you want to try to find the area of like a pie slice on that circle. Okay, so how are we going to use this with calculus? Well, looking at that little slice that I've drawn over here, this one here, this thing here, looking at that slice right there, that itself can be viewed as a sector, and we can even assume that this little edge right here is just perfectly like a little slice of an actual circle, okay? And again, this is a safe assumption. As long as that delta theta is small enough, then we can just assume that that little bit, that little red part there, actually is kind of a little slice of a circle. Even though it might not match the function exactly, it's going to be pretty close as long as that delta theta is small enough. And you can kind of think about the analogy between this and, you know, what we were doing with a Cartesian defined function. We had divided that up into a bunch of little subintervals, and if you look at just one of those with delta x, you know, at the top of that, we view it just as a straight up rectangle, right? At the top is just a straight side there, right? Of course, that doesn't match the exact function. It doesn't match the function exactly, right? But again, as long as that delta x was small enough, it's a pretty close approximation. Very similar here with this idea of this slice that we're looking at here, this sort of small pie slice that we're looking at here. So what's the volume of that little pie slice that we're looking at there? According to that formula back from trigonometry, it's going to be 1/2 r squared delta theta. Right? That delta theta is that just a tiny little bit that moves there. Okay, so now you can kind of maybe think about what what we would actually put here is like an r sub I, because that radius would be different if I, for example, drew it over here, right? And so then the idea is that we have a whole bunch of these little pie slices, and what are we going to do with them? Each one of them will have a different radius, right? That's why I call it r sub I, depending on which one we're looking at, right? And so what do we do with that? Then we just take a bunch of those and add them all up, and that gives us an approximation. So we could have oops, I shouldn't be putting volume of that, so I should be putting area, not volume. Sorry about that. It should be area, not volume. Yeah, so what you can then get from this is the approximation, and that would just be 1/2 times the summation from I equal 1 to n of these. The r is itself a function of theta, right? R is a function of theta. So really, what you could also put here is f of theta sub I, and then square that, and then multiply it by the delta theta. And then what's the next step? We want an approximation of this, or the exact value of this thing. So what do? We take the limit as n goes to infinity, and I'm going to skip that part of it, because what we eventually get is the exact area, right? The exact area. After we set up that, after we take the limit, we're going to get this integral, right? So we'll have 1/2 integral from a to b, and the a and the b are again these theta values, like theta 1 and theta 2, f of theta quantity squared, and then the delta theta becomes d theta. And so this is the formula then to find the area enclosed by some kind of polar defined function. Okay, so everybody see how we kind of arrive at this formula for finding the area enclosed by a polar defined function. What is it? Yeah, so you will be able to tell, because polar defined functions have r on the, usually r is like the dependent variable, almost always, and theta is the independent variable. So you'll definitely know that you have a polar defined function, because it will be r equals, and then on the other side you'll have some function of theta. Okay, so you'll just know by looking at it that it's polar defined. Okay. In fact, if you have messed around with Desmos much, Desmos just recognizes that you're talking about a polar function. If you put r equals something and then put a theta on the other side of it, it will know that you're dealing with polar, and it will just automatically switch over to that. Okay. Yep. And just like with we've talked about what the three, there's the Cartesian defined functions, there's parametrically defined functions, and then there's these polar defined functions, right? But they all have very specific forms to them, right? Like Cartesian functions, y equals f of x, or x equals f of y sometimes. For the parametrically defined ones, it was x equals some function of t, and then y is equal to some other function of t, so those ones are pretty easy to recognize as well. And finally, these polar ones use r's and thetas. All right, so let's do an example of this. Let's do example 1. This is telling us to find the area of the region that is bounded by the curve r equals cosine theta, where theta is between 0 and pi over 6. Okay, so they give us the bounds here, and we just have to use that formula then. We don't even really need to know what the function looks like, but if we want to, we can graph it and take a look. All right, so using that formula, just plug in what we need, right? We're going to have the 1/2 integral from 0 to pi over 6. It's r squared, so we have to put cosine squared here, and that's it. That's all we need. So that's the integral that we have to evaluate. What you're going to find in this particular section is that there are going to be a lot of trig integrals, just regular old trig integrals. So we definitely need to be up on that kind of thing. And so do we remember how to deal with a cosine squared if we want to integrate this? How do we find that antiderivative? What should we use? Power reduction identity, exactly. Plus 1/2 cosine 2 theta. Okay, and then we can just use our, oh, actually, let's go ahead and just factor out that 1/2, since we don't really, we can just take that out of there and do this. Okay, so that's going to give us 1/4 antiderivative of that's going to be theta, and then for the cosine 2 theta, we'll have a 1/2 sine 2 theta, and so that'll give us 1/4 pi over 6, and 1/2. If I plug in pi over 6 there, that's going to turn into the sine of pi over 3, right? So 1/2 sine of pi over 3, what's that? Root 3 over 2, right? Yeah, when we plug in 0, nothing's going to happen there, right? We'll just get 0 on both of those. So that's going to give us, for our final answer here, pi over 24 plus, let's see, that's going to be root 3 over 16, it looks like. And again, just to be clear about what we just did, let me go ahead and show you the graph of this thing on Desmos. Okay, so like I said before, if you want to graph something in polar form in Desmos, it's pretty nice because all you have to do is just, you don't have to like tell it that you're in a different graphing environment. You can just put r equals cosine, and then for theta, you can actually just type the word theta and it just understands. Kind of neat. So now looking at the graph, you see that it's a circle. Let's only go to pi over 6 on this, and you can see that arc right there. And so if you can picture what's actually going on here, if you have a line, in fact, let me go ahead and graph that line right there. Let's graph theta equals pi over 6. Oh, it doesn't like that. Oh, that's too bad. I was hoping that it would let me do that, but no, I guess it doesn't. Anyway, what I'm trying to get it to do is if I picture this line that goes from the origin out to that point right there, I don't know if you guys can see me move my mouse there, but it's that line right there. That would give you this sector, right? That would give you the pie slice. And then what we just found is the area of that pie slice. Okay, so occasionally you'll be asked to find the area between two polar defined curves, just like we did with at the beginning of this semester, finding the area of between two Cartesian defined functions, right? Area between two curves, in other words. So what do you do if you have that situation? Well, it's pretty similar to the way that we did areas between curves, areas between two curves. In this case, you might have one polar defined function that, I don't know, does something like that. Maybe you've got another one that, in fact, they could intersect. So you could actually do this as a different color here. So maybe you've got another function that does something like that. And this is maybe your f of theta function, and this is your g of theta function. And so what you do then is you want to think about, same sort of idea here. We'll have like an arc, a little tiny arc for one of the functions, and then we'll have another for the other function. Or basically you can just kind of say that this arc forms a little region here, right? When we are bounding one function, the one that's further away, minus the one that's closer. If you do that, then what you're going to get is this little bit right here, you see? And so that region there, the shaded region, is going to be, if I call this like our theta sub I right there, or delta theta, I guess, that's delta theta. This here, this particular angle that we're talking about is, let's say, theta sub I. Then that region, that shaded region here is going to be, its area is going to be 1/2, again, according to that formula that we saw from trigonometry, 1/2 f of theta sub I minus g of theta sub I multiplied by delta theta. Okay, and then again, if you can extrapolate this to the formula for finding the area between two polar defined curves as a is equal to 1/2 integral from a to b of f of theta minus g of theta. Yeah, that should be squared. That should be squared. Yep. And this should be squared too. Okay, so that's it. That's the formula. And again, you can just kind of compare that to what we saw in areas between regular curves, Cartesian defined curves. It was very similar, right? It was one function minus the other one. The only reason these ones are squared again is because of that formula for finding the area of a sector. All right, so let's try example 2. So this says find the area that lies inside the first curve and outside the second. So these ones can be a little bit confusing to graph. It's also kind of difficult to visualize these polar defined graphs. Again, with Cartesian defined graphs, we've used them so much that we're kind of familiar with some of them, right? Like if I say, here's a cubic function, you kind of know what it's going to look like, right? if I say here's a square root function, you kind of have a little bit of an impression about what it's going to look like. When you see polar defined functions, they're pretty new, and we don't use them very much. We haven't yet used them very much. So it's kind of hard to tell what they're going to look like. So graphing calculator is almost invaluable on this kind of thing. So in fact, I'm going to go ahead and open the graphing calculator, and we'll graph it on there so we can kind of get a sense of what that region is going to look like that they're talking about here. It says find the area that's inside one curve and outside the second one. So let's go ahead and, well, actually, before we do that, let's find the points of intersection on these two curves, because that's going to be important. Where do these two curves intersect each other? And to do that, we do exactly the same thing that we would in Cartesian defined functions. If I want to find points of intersection, I set one function equal to the other one. And so I'm going to do the same thing here. And so this actually gives us sine theta is equal to 0, I think. And so we just have to say, okay, well, where on the unit circle is the sine of theta equal to 0? Well, that would be at 0, right, and at pi, I think, those two places. So what we're probably going to see when we actually do graph this thing is that it will intersect at those two values of theta. So let's take a look at the graph real quick. Let me open my emulator. Okay, so I'm going to enter both of these polar defined functions, 1 minus sine theta. Okay, my window's not that great here. I'm going to change the window to -3. I'm just going to try this window and see what it looks like. -3 to 3 and -3 to 3. Let's see what that looks like. So that graph, if you see what that kind of looks like, a heart, that's a cardioid. I'm going to go ahead and zoom in a little bit. Okay, so there we go. That's the two graphs. You can see the circle. That's the second thing that was graphed. And you can kind of also see that they intersect. Indeed, where do they intersect? It seems that they're intersecting at the positive x-axis, right? And then also at the negative x-axis. Well, what two angles are those? That's 0 and pi, right? So let me go ahead and graph this on the whiteboard. All right, so this is kind of what we had. We had a cardioid and we had a circle, and they intersected at that positive x-axis and at the negative x-axis. So I'm graphing a little bit wrong here. The cardioid actually comes down here, and the circle intersects here and here, something like that. So there you can kind of see the points of intersection are right here, right, this one right there, and then right there. And that corresponds to theta being 0 and theta being pi. What you're also going to find on these particular problems is that there's often a lot of symmetry that you can take advantage of, sometimes more than one symmetry even. And so whenever you see it, take advantage of it. So does everybody kind of see what is the region that we're actually looking for here? It says find the area of the region inside the first curve. The first curve is that cardioid, right? So inside that, but outside of the circle. So if I were to shade in the region that we're actually looking for, inside the cardioid and outside the circle seems to be all of this. And then once you've decided that that's what the region is, then you can say, okay, well, where does that region begin? Like, for what value of theta does that region that we're looking at actually begin? Well, it seems to start right here at theta equals pi. Right? At theta equals pi, then after that, then the cardioid graph will follow this, right, for those values of theta between pi and 2 pi, and then it will end right there. For values of theta that are bigger than pi, the circle will begin here, sweep through all of this, and then it will intersect again once we sweep over to 2 pi. So it looks like the bounds of this thing are pi and 2 pi. However, if you notice, you can take advantage of symmetry with this one as well, because that region that's to the left of that red line right there is going to be, so in other words, all this stuff here is going to be the same as all of that there, you see? So there's definitely symmetry going on here. And so what we can do to take advantage of that symmetry is we can double the integral, and we can go from only pi to 3 pi over 2. Everybody see what I'm talking about with that? So that we can say that the area in this case is going to be 1/2, or actually, since we're using symmetry, I'll just go ahead and write it 2 for the symmetry, and then the 1/2 is coming from the formula for finding these areas, right? integral from, let's go from pi to 3 pi over 2. And then the bigger function here, the one that's farther away from the origin, is the cardioid. So that one we'll put first, 1 plus cosine theta. And then we have to square that. And then minus the other one, the one that's, oops, no, I'm sorry, I'm looking at the wrong problem here. 1 minus sine theta, I mean. 1 minus sine theta, square that. And then the other function is just that constant function 1. So 1, and then that has to be squared as well, but it doesn't really do anything, but I'll put it anyway. So the question is, do we usually want to take the left side bounds of a symmetrical integral, or does it depend? Yeah, it really actually doesn't matter. Like in this case, you could have said just as easily, you could have started this integral at 3 pi over 2 and ended it at 2 pi. It really doesn't matter. So yeah, to answer your question, in this case, it really doesn't matter at all. And some of them, it might actually be a little bit easier to pick one over the other, but usually it doesn't matter at all. Okay, so I just did it since it's the first one. It started at pi and ended at 2 pi, so I figured I'll just use the first half. Okay, so there we go. That's it. So the 2 and the 1/2 cancel. Let's go ahead and expand this, squaring that. 1 minus 2 sine theta plus sine squared theta. And then we have the minus 1 on the end there. Okay, then the 1 minus 1, those cancel nicely. And then for the sine squared integral, you do a power reduction identity. Oftentimes, just by the nature of this particular formula, in fact, the fact that it's r squared, we're probably going to be seeing a lot of sines and cosines being squared here. So we definitely need to know how to deal with that. And then the sine squared, we'll use the power reduction identity on that. For sine squared, it's 1/2 minus 1/2 cosine 2 theta. So that's the integral that we need to find. Okay, so antiderivative of negative 2 sine is going to be positive 2 cosine, and then plus 1/2 theta, and then antiderivative there, we're going to have a minus 1/4 sine 2 theta. And then plug in our two bounds, 3 pi over 2 pi. Yeah, in this case, I'm not even sure. It might have been easier to just not even do the symmetry on this. We could have just gone from pi to 2 pi. I'm not sure it would have made it any more difficult. So in this particular case, I'm not sure that symmetry really benefited us much, but it's good to at least point it out because sometimes it really does benefit us. So if I plug the 3 pi over 2 into there, I get cosine 3 pi over 2. The cosine of 3 pi over 2 is 0, right? So we're just going to get a 0 there. Plus 1/2 times 3 pi over 2 minus 1/4. Now when I plug in 3 pi over 2 there, those 2's are going to cancel, so I'm going to get sine of 3 pi. But sine of 3 pi, that's just, that 3 pi is going to be the same as pi, right, as far as its location on the unit circle. The sine of that is 0 also, so we're going to get a 0 there too. And then when I plug in pi, we'll say minus the cosine of pi, 2 times, let's see, the cosine of pi is negative 1, right? So get that, and minus 1/2 pi, and plus 1/4 the sine of 2 pi. The sine of 2 pi is 0 also, right? 2 pi is 0 also. Okay, so let's see. Some of these were 0. That's gone. That's gone. That's gone. Those terms that have 0 are all gone. So we're going to be left with 3 pi over 4 and plus 2 and minus pi over 2. And those are like terms. So that's like 2 pi over 4. So 3 pi over 4 minus 2 pi is pi over 4, right? So we get pi over 4 plus 2. So what we, again, just found here, just to be clear, we put the beard on this guy, and we found all that. Okay, find the area of the region that lies inside both curves. All right, so this is number 3. R equals 1 plus cosine theta, R equals 1 minus cosine theta. So if you have a calculator, go ahead and try to graph that. I'll just show you what it looks like real quick, and then I'll try to draw it again. 1 plus cosine theta. Second one, 1 minus cosine theta. And let's see what it looks like if we need to change the window. Okay, so that looks like a cardioid there and another cardioid. Cool. plenty of symmetry going on there. So let's see how we might approach this particular problem. All right, so the first graph we said looks like some kind of a cardioid right there, and then the other one, put that in a different color, basically is the same thing, but kind of like a mirror image of it, right? So that one does something like this. And we are trying to find, what are we trying to find here? The area that's inside both of them, okay? Inside both of them would be this, right? All of that and all of that. So any questions about the region we're actually looking at here? It's pretty important to try to look at the graph first and just see if you can identify what the region actually is. All right, now to continue, we want to be thinking about the points of intersection here. Although, if you think about this problem, if you kind of just look at what's going on here, you might actually find that we don't even need to use both these functions. Like, look what I'm talking about here. For example, on that blue graph there, right? On the blue graph, let's see, the blue graph is this one here, right? The 1 minus cosine. Notice that when theta is equal to 0, what do you get there? You get r equals 0, exactly. So that means that this graph starts here, and as theta gets bigger, it sweeps out this curve here. So basically, once we reach right here, the top there, we've swept out between theta equals 0 and straight up. Straight up is pi over 2, right? But look at the region that's actually been swept out by doing that. You see that? That's what you get when you sweep that first graph from 0 up to pi over 2. You see that is the region that's enclosed, that little part in red there that I've shaded in. But if you look at that region, isn't that like part of what we're trying to find anyway? In fact, if you look at it, that's exactly 1/4 of what we're trying to find anyway, right? And so since there's so much symmetry in this graph, and basically one graph is just a mirror image of the other one, all we really need to do is just find the area of that second graph between those two bounds that I just said, 0 and pi over 2. So the total area that we're actually looking for here is actually 4 times the formula that we would normally use, 4 times the integral from 0 to pi over 2 of just that second area, 1 minus cosine theta. And then, of course, we have to square that because of the formula. Does everybody kind of see what I'm talking about there? And why we were able to, by carefully looking at the graph, deduce that we actually didn't even need to use the second graph at all here. Yes, we're only using one graph because this thing has basically all kinds of symmetry going on, right? It's got symmetry across the x-axis. It's got further symmetry across the y-axis. And so since the graph that we're looking at, the blue graph, basically just going on that little quarter of it, would be exactly the same thing as if we looked at the black graph and started at pi over 2 and then went over to, I guess, 3 pi over, or probably to pi. And so we don't even need to worry about that second graph. All we need is just this one little region. Okay, so let's go ahead and evaluate the integral. We'll get 1 minus 2 cosine theta plus cosine squared theta. And again, here it is again, right? Pretty much on all of these problems, we're dealing with that second power of sine or cosine, right? So we're seeing a lot of that power reduction, the necessity of that power reduction formula. So we'll have to put that here. So we're going to get 1/2 plus 1/2 cosine 2 theta. Now, when you're using that formula, I would definitely recommend that you simplify this as much as you can after you've used the formula. Just, in other words, look for like terms. And there are like terms here, right? The 1 and the 1/2, so we get 3 halves there. And then maybe to avoid fractions here, if you wanted to just not have fractions, at least in the integral itself, you could go ahead and distribute that 2 that's out front, and then we'll get 3 minus 4 cosine theta plus cosine 2 theta. All right, then we can go ahead and find our antiderivative on this thing. 3 theta, antiderivative of cosine is sine, so we'll have minus 4 sine theta, and then here we'll have 1/2 sine 2 theta. Okay, then plugging in our bounds here, we get 3 pi over 2 minus 4 times the sine of pi over 2. Sine of pi over 2 is 1, right? So 4 times 1. If I plug pi over 2 into the other one, those 2's are going to cancel into the last one. The 2's will cancel, so I'll have the sign of pi there. The sign of pi is 0. I'll write it anyway so that we see exactly what's happening. Now when I plug in 0 there, I don't think we get anything, right? Because plugging in 0 here, we get nothing. Sine of 0, 0, sine of 0, 0. So those plugging in 0 gives us nothing. And so what we get at the end of this seems to be 3 pi over 2 minus 4. All right, so definitely try to take advantage of symmetry as much as you can. Like this problem here, I think the question was, how do we know like which symmetry we should use, or if we should use it at all? In that first problem, it probably wouldn't have mattered even if we didn't notice the symmetry. Here, it certainly it would certainly be beneficial to us to notice that symmetry. All right, example 4 here, we're putting this on here because there's something that we kind of have to be aware of with polar defined graphs. And the issue is that I think I've mentioned this, that we have multiple representations of the same point, right? It's possible to represent really any point in the xy plane in multiple ways using polar form, right? And so it turns out that you can actually represent the same function in different ways with polar form, okay? For example, so that r equals 1 in particular, this one, there's another way to represent that exact same function, right? Like, remember that a constant function, what does it look like in polar form? It's a circle, right? But what if I wanted you to graph the function r equals -1 instead of r equals 1? Well, that would be the same graph, because any point that has a radius of -1, remember what a negative radius means, that just means that when you're pointing at any particular angle, you don't go in the direction of that angle, you go in the opposite direction, right? So if you have a function that's r equals -1, it would be the same exact circle as r equals +1. And so keeping that in mind, let's see, the goal here again is to try to find all points of intersection of these graphs, right? That's an important thing to be able to do, because when we're trying to find the areas between two graphs, we need to know where they intersect, because that's going to like be the bounds of the integral that we're setting up, right? Like the first point of intersection, that's the lower bound. Second point of intersection, that's the upper bound. So in order to do that, we need to set one function equal to the other and then solve. And so here again, we have to kind of remember, how do we solve trig equations? Well, to solve this particular equation, you can divide both sides by 2. You can get sine 2 theta is equal to 1/2. And again, this is like hopefully a review from trigonometry. This is an important thing to be able to do. And you guys have seen it already, theoretically. The way that I approach this type of problem is I say let's let u equal 2 theta. And then I solve this equation. Sine of u is equal to 1/2. And let's solve that. Where is the sine of u equal to 1/2? For which angles is that true? Let's see, the sine being 1/2, that occurs at pi over 6, right? And let's go ahead and not forget to put the plus 2 pi k on there. You remember that from your pre-cal. And then we also get u equals, let's see, where's the other place where the sine is equal to 1/2? That occurs in quadrant 2, right? Because that's where the sign is also positive. I believe it occurs at 5 pi over 6. And then let's not forget to put the plus 2 pi k on that as well. Because it says here what we're trying to do is find all points of intersection. That would be any value of theta for which this is true. Then the way that we solve this for theta is we go ahead and plug back in the 2 theta, because that's what we said u was. Okay, so 2 theta is now equal to pi over 6 plus 2 pi k. And 2 theta is now equal to 5 pi over 6 plus 2 pi k. Then we just divide by 2, and we get theta is equal to pi over 12 plus pi k. And here we get theta is equal to 5 pi over 12 plus pi k. Now, thinking about on the angles that are on the unit circle where this is occurring, because really the unit circle is all we really care about when we're looking at, areas for these types of graphs. So on the unit circle, let's write out all the solutions that we have. Let's see. On the unit circle, well, the first one's going to be pi over 12. Theta equal pi over 12. And then we've got 5 pi over 12, right? That's clearly two solutions. Well, what about if theta or k is equal to 1? Then we get pi over 12 plus pi. And that's 13 pi over 12, I think. And that's definitely still on the unit circle. It's just a little bit bigger than pi in quadrant 3. Then the other one, if I say, again, I'm looking at the k there, if k is equal to 1 there, then I get 17 pi over 12, right? And that is still on the unit circle. Anything up to 24 pi over 12 is still going to be on the unit circle. So what we have is 4 points of intersection, okay? 4 places where these two functions are going to intersect each other. But let's take a look at the graph and see if that really happens. Okay, this is the point of this problem, is to just notice that there's a bit of an issue that we have to deal with when it comes to polar functions and finding points of intersection. All right, so I'll take a look at the Desmos graph for this thing. Let me open that. So let's look at those two graphs, those two functions, and see where they actually intersect. So 2 sine 2 theta. Theta between, we should probably go all the way to 2 pi on this one. So there's the graph. It looks like a nice, I think they call that a rose for the shape of the graph. Then the other graph is just r equals 1, so constant function. Okay, so look at how many points of intersection we actually have. Well, let's see, there's one right there. That one there is, anyway, you can see the first place where the green graph intersects the red one right there. That's got to be pi over 12. The other ones that we saw were, 5 pi over 12. That's got to be this one over here in quadrant 2. 13 pi over 12 and 17. So 13 pi over 12 is a little bit bigger than pi, so that must be this one here, down here in quadrant 3. And then there's got to be that 17 pi over 12 got to be this one here. So it seems that we've gotten all 4 of these solutions that are the closest to the x-axis, okay? But what about these other ones? Where the heck are those coming from? There's actually 8, right? But we've only found 4 of them by doing what we thought we were supposed to do, just to figure out points of intersection. So where are those other solutions? How do we find them algebraically? Well, again, it actually comes from the fact that there are these multiple representations of the same function. That's the problem here, is that there's other ways to represent that same function. We have to, if we want to find these points of intersection, we have to think about all possible representations of these functions. And so the other 4 solutions that we're not seeing from our algebra here are the fact that that one function, r equals 1, can also be represented by a different function, a different equation, by r equals -1, okay? Now, if that's the case, then we also actually have to solve this other equation here. 2 sine theta, or 2 sine 2 theta is equal to -1/2. Oh, sorry, -1, I mean, and then I'm getting ahead of myself, -1. And then we divide by 2 and get sine 2 theta is equal to -1/2. So that's where those other 4 solutions are going to come from. And if we kind of just follow what we did before, where is the sine of theta equal to -1/2 now? Well, I'm going to skip the u part and just say 2 theta is going to be equal to, let's see, where does that happen? 7 pi over 6, I believe, is one of them. 7 pi over 6. And you got to put your plus 2 pi k on there. And then the other one, where this is equal to -1/2, be 11 pi over 6 in quadrant 4. And then division for our last step gives us the other 4 answers, or at least a way to get the other 4. 7 pi over 12 plus pi k, and 11 pi over 12 plus pi k. And then again, letting on the unit circle, the ones that we really are interested in, letting k equal 1, well, letting k be equal 0, you get these two, right? You get theta equals 7 pi over 12 and 11 pi over 12. And if theta is equal to 1, then we add pi to that, you get 19 pi over 12. And the last one, you get 23 pi over 12. So I think I might have said that wrong on the graph. Actually, that 23 pi over 12 is the one that's going to be closest to the x-axis. I guess the other one that we had, 17, was actually that one that was down also in quadrant 4, but just closer to the 3 pi over 2, the y-axis.
Actually, I think
so anyway,
the first set of solutions that you got were in the first quadrant and the third quadrant.
Oh, okay. Is that what's happening? Okay, cool. Yeah, that makes sense. Yeah, because that's where, yeah, I guess that matches the signs. Yeah. Okay, so first quadrant and third quadrant were these first set of solutions, and then the second set gave us the second quadrant and the fourth quadrant. But anyway, now we see that there are actually 8, right? And now our algebra is verifying that. We just have to realize that we also had to consider the r equals -1 on there. Okay, so again, the point here being that be careful with the algebra on finding these points of intersection. You have to think about these alternate representations of the functions. That's all that we were actually asked to do on that problem. We're not asked to find any areas or anything like that. Okay, then the last thing on this section that we need to talk about is arc lengths in polar form. Like, how do you find the length of an arc of a function in polar form? So we'll do that, and then we'll be pretty much done with this section. All right, so this is arc lengths in polar form. What we need to do here is realize that we're going to use that parametric idea that we did before, but here we have to realize that x is equal to r cosine theta and y is equal to r sine theta. But we do have to remember that r here, since we're talking about polar form, has to be viewed as a function of theta, right? R is equal to f of theta. And so what we can do here is think about the arc lengths in parametric. And we derived the formula for that. It was, I think we used alpha and beta, but it doesn't really matter here. And then we had dx dt. I'm going to say that theta is the parameter here, so I'm going to call it dx d theta squared plus dy d theta. So remember, in parametric form, these thetas were actually t's. But what we're kind of viewing here is that when we're talking about polar form, we actually do have a parameter here, and that parameter is actually theta. So what we're doing is just saying, okay, we're parameterizing this in a very special way. The way that we're parameterizing it is right here. This is the parameterizations right here. So if we stick with those, then we can put this into a formula for arc lengths in polar form. So how do we do that? Well, we have to figure out what dx d theta is. So dx d theta is actually, we have to look at this, the derivative of x with respect to theta. And so for that, again, realizing that r is a function of theta, we then have to view this thing as a product. This has to be viewed as a product, r times cosine theta. Okay, so when I take that derivative, I would take the derivative of the first one, derivative of r with respect to theta. That's dr d theta times cosine theta. This is the product rule that I'm using here for derivatives, right? Derivative of the first times the second plus first function times the derivative of the second. So that's going to be r. Derivative of cosine is negative sine. So in fact, I'm just going to put the negative here. And then dy d theta, we're going to need that too. Again, very similar. That's it. And we have to view that r sine theta as a product. So dr d theta sine theta plus r cosine theta. So this actually turns out to be kind of a mess to simplify or to derive the formula, and you might be able to see why this is going to turn into a big mess. Because look what we have to do now. We're going to now take these two things, right? This is where they are, right? And we got to square them now and put them under that radical. So that's what's going to happen next. We need to, if I square this thing, dx d theta squared, that means I got to square this whole thing. And so what's that going to do? We'll get dr d theta squared cosine squared theta. The combo of these two is going to give us two of those. So 2r dr theta sine theta cosine theta. And then the last term is going to give us r squared sine squared theta. Okay, now let's look at the dy d theta terms and square that. Dy d theta squared. So that's similar. We're going to have this. Square that. We'll get dr d theta squared sine squared, and then the combo term will be plus 2r dr d theta sine theta cosine theta again, and then the last term is plus r squared cosine squared. All right, now look what happens when you add these together. So I'm just going to do this vertically to save some writing here. What happens when I add all this together? Look what happens to the middle term. Boom, they're equal and opposite, right? And look what happens to this first term here. We're going to get dr d theta squared, and then we'll have a sine squared plus a cosine squared, right? Sine squared plus cosine squared. And then look at the last terms, plus, what are we going to get there? We're going to get an r squared, and we're also going to have a sine squared plus cosine squared, right? So it is a big mess to do all this, but what do we end up with at the end? It's actually pretty nice, right? Look, that's 1, right? This is equal to 1. And so is this. This is also equal to 1. And so what we get at the end of this is dr d theta squared plus r squared. All of that stuff simplifies. And so again, this is what's under the radical up here for that arc length and parametric form. So what's the outcome here? The integral from a to b of dx d theta squared plus dy d theta squared, as long as we use this particular parameterization that we talked about for the polar form, what does it end up being? It ends up being that nice little formula that you see on the page and what we just derived. R squared plus dr d theta squared. So there it is. There's the formula for the arc length in polar form. So let's go ahead and just do the one example for that. Let's try example 5 here. This is again just demonstrating how to use that formula. R is equal to 2 cosine theta. Now in this case, we don't really even care what the graph looks like because we're just using a formula. So here theta is between 0 and pi. So here all we got to do is just use the formula. And so that formula requires a dr d theta, so we got to find that. So dr d theta in this case is negative 2 sine theta. And so the length of this arc must be the integral from 0 to pi of, according to the formula, again, it's r squared, so we'll have 2 cosine theta squared, that's the r squared part, and then the dr d theta squared, that's the minus 2 sine theta, and we've got to square that, and then simplify this, we're going to get 4 cosine squared theta plus 4 sine squared theta. Well, look at that. You can factor the 4 out of there, and what are you left with? Cosine squared plus sine squared, right? That's just 1. And so what we get there is just 4 under the radical. So in fact, at the end of all this, we just get 2. And since it's a constant, you can pull it out. And the only thing that's left after taking that root is just d theta. So this is really nice. This one turns out to be about as easy as we can hope for. And so we get 2 pi for our answer here. So the length of this arc of this particular function, this polar function, r equals 2 cosine theta, between 0 and pi, the length of that arc would have to be 2 pi. Let me go ahead and show Michael's solutions here. If you guys want to at least take a look at those problems there at the end, problems 1 through 4. Okay, so there's the solutions. So there you go. Now you have all the solutions to those problems. Yeah, if you guys notice on that second problem there, you see that there is symmetry here, right? Like basically everything between there and there is going to be identical to going down to there. You see what I'm talking about? So that's what he's doing there. That's symmetry that you can take advantage of. So anyway, there's symmetry you can use there. All the other ones, yeah, if you look at that fourth problem on there, I think that ends up being kind of a pain, doesn't it? Oh no, it doesn't. That was not too bad. I know on some of these, like, the problem looks deceptively easy. Like, if this was just r equals theta, probably about the simplest spiral function you can get. It turns out that to find an arc length, you actually have to use trig substitution to do that. So, and I think the trig substitution ends up actually having a secant cubed in it, which, if you remember, is a real pain integral to do. But this one's not that bad, the last one there, because it looks like you can just do that by regular substitution.